Here we go. So we're live and we're recorded. So what I would like to start with is not the main topic of today, which is Stokes flow with Low-Reynolds numbers. I would like to start with the end of last week's lecture, which is actually not the one I just loaded. Sorry. It's actually lecture number 4, exact solutions. Because we went as far as all the steady flow solutions. Let me share the screen so you can see the same thing as I can see. Sharing screen. Here we go. So these are the slides from last week. We went through a bunch of exact solutions. Flow between two flat plates with a plate moving on top with velocity u and possibly pressure gradient. We solved this on a blackboard, came up with one special case Couette flow, which is probably the simplest exact solution of Navier-Stokes. It's a linear flow profile, velocity profile, and it's there if you have zero pressure gradient from left to right and a moving wall with velocity u on top. Then the other special case is when you have no moving wall or both walls are staying put, and you have a pressure gradient going from left to right. And of course, you can have combinations of the two. And then we looked at the flow between two rotating cylinders, which is actually quite similar to the flow between two flat plates, except that everything is done mathematically in polar coordinates, so it becomes a bit more tedious when you solve the equations, but at the end it's technically the same story. And the interesting thing, and something I really want you to understand, is that the two fundamental parts of this solution, can you see my mouse pointer on the screen? Yes? Okay, so we have one part of the solution is A times R, A being an integration constant is given by the boundary conditions, and the second one being B over R, being the other fundamental solution, are two well-known solutions that we talked about before in the lecture on flow kinematics. And we actually looked into this last week. A times R is like a solid body rotation, so it's what you get if you have a bucket of water rotating steadily for a long time, and the whole fluid is rotating, is moving as if it was a solid body rotation. And the second term is what we call an ideal vortex. It's the vortex without vorticity. You can go in your textbook or in your notes and find the definition for the vorticity in polar coordinates and compute the vorticity for this term B over R. And you will see that independent of the value of B, it is always 0. So the second term has no vorticity in it. And these are the two images that relate to that: the ideal vortex without vorticity on the left, and the solid body rotation with vorticity on the right. And these are two special cases of this general solution of the flow between two cylinders. And then the third type of flow that we studied last week was the Poiseuille flow, maybe one of the technically, also biomedically most important flow solutions. Also an exact solution of Navier-Stokes. And we didn't go through it on the blackboard, but it works out quite similar to what we did for the flow between two flat plates. And we end up with what is known as the Poiseuille flow. Again, a parabolic velocity profile proportional to the proportional to the pressure gradient. And if we integrate the velocity profile over the whole cross section, so we're not looking at the velocity itself, but at the integral of the velocity profile over the cross section, then we obtain a volume flow rate. So how many cubic meters per second, or how many liters per minute, or whatever units you choose, are transported through this pipe. And we call this usually q with the variable q, and it's given by this formula. Sorry, back by this formula. And the important or the physiologically relevant thing here is that we have the radius a to the 4th power, right? Which tells us that by changing the radius, we have a very strong tool or strong means to modify the flow through a vessel. Or if you wanted the resistance of the vessel, can be very effectively changed by changing the radius. And then we came to unsteady flows, and actually I did not have the time to do that. And I would now like to do on the blackboard a little derivation or part of the derivation for the Stokes boundary. And actually, if I have not done so, there's also a nice, let me switch off. Oh, by the way, can the students see me on the little icon on the right when I'm talking? Okay, good. Yeah, I will still switch off the slides now and go over to the blackboard view. There's quite a nice representation of that in Kundu and Cohen. And can I please remind me to upload this? I have not done so yet. So essentially what I'm doing now is written here on 1 to 2 pages. But still, I think it's worthwhile to go through that together because it's an important concept that you understand. So what are we doing here? So we're looking at the flow over a plate, over a wall. So we have a wall here on the bottom, and this wall will be moving to the left and right. So it's oscillating forth and back with a certain frequency omega. And we have a wall normal coordinate, which we call y. And the wall will be moving to the right. The wall will be moving to the right with a maximum velocity of plus u, and likewise move to the left with minus u. And what we're interested in is understanding what the flow field looks like. And I can already tell you that we will obtain a flow field which roughly looks like that. So close to the wall, the velocities will be, or the fluid will be moving with the wall in the same direction as the wall is moving, if it's moving to the right, as in this case. And somewhat above will be moving to the left, then to the right again. So it's just like it looks a bit like a wave. And of course, this pattern is changing. If the wall, this is the time when the wall is moving to the right. When it's moving to the left, you have the opposite picture. So you will have something like a wave shape traveling upward and oscillating in time. So quite a complex flow field. And what we will also see is that the speed of decay, let me indicate this sort of by the amplitude here. So this is decaying, the amplitudes are decaying, they're oscillating, but there's like a maximum amplitude, and the rate of decay, or let's say a typical thickness of this situation, let me do this in yellow, the typical thickness delta will scale with 1 over the square root of the frequency omega. So that whole thing, this velocity field decays exponentially as we go away from the wall. And this creates typical thickness of 1 over frequency square root of omega. So it means farther away than this thickness, this will very rapidly or exponentially fast go to 0. So that means that this effect, these velocities here, for very high frequencies, we only see them very, very close to the wall, a very thin layer close to the wall, and farther away from the wall, we'll see nothing. Whereas for very low frequencies, for a very slow moving wall, this layer becomes very, very thick. And in the extreme case, where the velocity will go to 0, this layer becomes infinitely thick, or essentially the whole fluid will move with the wall. This is a quasi-steady situation. Now, how do you get this result? And I will just try to hint to you what the derivation will look like. So what we can formulate is the momentum balance in y direction. Or actually the Navier-Stokes equation in the y direction. Move this up a little bit, just like that. And sorry, I was wrong, not in the y direction, in the x direction. I'm sorry. So for the velocities u, this velocity field u of y and t. U and y and t. And we formulate the momentum balance in x direction, so for the velocity. So if we look at our Navier-Stokes equation, we have a rho times du dt plus a nonlinear term, gradient of u, and here's the vector, but here's only a velocity u because we're only going in x direction, is equal to the pressure gradient in x direction and the viscosity times Laplace of u. Now, what can we do with this equation? There's a lot of things that we can drop. And without going into details, but if you were working out all the single terms, you would see that mainly because you have an invariance in x direction, this is infinitely large displaced, this term will identically drop out. So we don't need to worry about this ugly nonlinear term. Likewise, we skip this term. And why do we skip it? Because we say, this is now a definition, a boundary condition. We say there's no pressure gradient here from left to right. The pressure is the same in every direction. We're not applying a pressure gradient from the outside. So there's actually relatively little that remains in the equation. And let me write it down again. What remains, it's a rho du dt equals mu, and from the Laplacian, it's also, there's a second derivative in x direction, and that will also drop out because we have no change in x direction, right? Everything is the same in x direction, it's invariant in x, so we just have the second derivative in y direction. This is the only thing that remains from this equation. Some of you might actually recognize this equation. if you forget about fluid mechanics for now, this looks a little bit like the heat equation or diffusion equation. If U was a temperature or a concentration, here you have a second derivative and here you have a time derivative. This is like diffusive transport of information. In terms of fluid mechanics, it's not a diffusive transport of temperature or of concentration. Here, it's diffusive transport of momentum. So what the wall is doing, the wall is actually diffusively, or the wall is, by moving forth and back, the wall is introducing momentum into the flow field above the wall. And this term here, this second order term, is diffusing slowly the momentum into the fluid. And it's doing it, the faster, the higher the viscosity is. So we can understand this viscous term as something like diffusive transport of momentum. And now it should also start to become clear why we have this thickness, this boundary layer thickness. The viscosity tells us how fast this is moving in. At the same time, if the frequency is too high, the velocity with which the momentum is transported into the fluid is too slow. So by the time the fluid particles appear, notice that something is moving in the wall. The wall is already moving in the opposite direction. That's how this wavy motion is coming about and why it's slowly traveling upward. It looks like a wave traveling into the fluid. Now, together with this equation, there's also boundary condition. Boundary conditions, namely U at y0 of t is equal to U times cosine omega t. This is essentially just describing the oscillating wall. The solution of this equation is just something you learn in a calculus class. It's relatively straightforward. You can look it up in books. I just want to write down the solution for you. The solution looks as follows. We have U of y and t. You can see, so see that U of y and t is equal to U times e to the minus y square root of rho omega over 2 mu. Can you see this on the? Yeah, I think you can see. Yeah, this should be it. Okay. Times cosine omega t minus y. And again, same square root rho omega over 2 mu. This is the solution to this partial differential equation. And it looks quite complicated. But if we look at the different terms, I think you will see it's actually not as complex as it looks in the first place. First, we have this variable u in the beginning, and we see that at the wall y is 0, so this term goes to 1 here. E to the 0 is always 1. So we essentially just, and here it's also 0. So essentially we just have u times cosine omega t. Yeah? So this is essentially the boundary condition. This blue thing here is essentially our boundary condition. And as we go away from the wall, certainly this term here will do something to the phase of this oscillation. So this is something oscillating with omega t or with frequency omega, and the phase of the oscillation is changed, is shifted progressively as we go away from the wall. So shifting a phase, that's exactly what we see here. Everything is oscillating here. All velocities are oscillating with frequency omega, but at a certain phase shift. And the phase shift is changing as we go away from the wall. So this is what this term here is doing the phase shift. But I think the most interesting term, and let me mark it in yellow here, is this term. What is this term telling us? This is an exponential function decaying in y direction, so decaying as we go away from the wall. And this is modifying the amplitude, or we can think of the whole thing here as the whole amplitude. The amplitude is u times this e to the minus something function. At the wall, this is 1. As we go away from the wall, this is decaying exponentially. So this term here is actually this exponential decay. This is telling us how quickly the amplitude is decaying as we go away from the wall. And the scale, the speed with which it decays is given by this parameter. And we see here we have a square root and omega in it. So the inverse of it is like a length scale. And this is exactly why I have written here the thickness goes like 1 over square root of omega. This comes exactly from this term. There's one more thing I hope you can recognize in this term here. Let me write it out again here. So this term is rho omega over 2 mu. Let me write just above it the definition of the Wormsley number. The Wormsley number is A over sorry, now I'm missing things. Sorry about this, just a second. Rho omega over 2 mu. Yes. Yeah, the Wormsley number is rho omega over mu. So this is Wormsley. You should see now they're almost the same except for the factor of 2. Well, but that's just a factor to make it a bit thicker or a bit smaller. So essentially a factor here, the factor down here in this equation has something to do with the Wormsley number. And we can also say, looking at this, that the thickness or how fast this decays, the thickness of this layer is something that scales like 1 over alpha. It also tells us that if the viscosity is higher, the Wormsley number becomes smaller or the layer becomes thicker. So viscosity makes this layer become thicker and frequency makes this layer become thinner. That's exactly the balance that the Wormsley number is doing for us. Okay, so I hope this is clear. I hope this is recorded. Otherwise, we can take some photos and put them online. Let me switch back to to the slides. Yep. So you should see exactly the same thing here again. We have our oscillation, we have our equation, you have up here again this term here, omega over 2. Here they use nu, the kinematic viscosity, which is just mu divided by rho. So that's why we have a rho here and a mu here. So this, by the way, has a name. It's called the Stokes boundary layer. It's the boundary layer coming up when you have an oscillating wall. That's the name of this boundary. By the way, also an exact solution of Navier-Stokes. Now, last thing I want to do for unsteady flow is unsteady pipe flow. And that is not so different from what we just did. And I just think that instead of having a flat wall and a lot of fluid or an infinite amount of fluid above it and the wall is oscillating, we now have a pipe, and confined in the pipe, we have a fluid and the pipe is oscillating. So the pipe wall is oscillating, or now think you're not, well, think you're sitting on the pipe, you're moving with the pipe, then the pipe is not oscillating, it looks like the fluid is oscillating, okay? So if you go through this thought experiment, then you have exactly like pulsating flow in a pipe, you have like the flow you would find in an artery, in the aorta. That's where you have a pulsating flow in a pipe. We can go through the same process as what we just did, or a similar process of what we did when we went for Poiseuille flow, and we would end up with this equation. On the left-hand side, we have the unsteady term. Here we have the pressure gradient. And here we have the viscous term in radial direction in polar coordinates. This time we don't drop the pressure gradient as we did before. Before we said we have the wall moving and no pressure gradient. In this case here, we say the wall is steady, but we have a pressure gradient pulsing. And again, we assume a frequency for the pressure gradient. We can put this in and solve the equation, which we're not going to do. I'm just showing you the solution. The solution will look exactly like that. It's a Wormsley flow profile. Here you have the velocity, W, the actual velocity, is a function of radius and time, and a quite complicated equation here on the right-hand side, with a funny function, J0, which is actually the name or the symbol for the Bessel function of first kind of 0th order. So Bessel functions are ugly things. There's multiple Bessel functions, right? It's first kind, second kind, and so on. Here we just need the first kind. You can think of them as something like a sine or a cosine function. You have them plotted here on the right. They're a bit like sine, or actually when you look at the red line, this is the one that we have, the J0. It's like a cosine function that is decaying. I think it's decaying like 1 over x or something like that, 1 over square root of x. But that doesn't really matter. What really matters is that, again, in the argument, just as before, we find the Wormsley number in here. Here's the Wormsley number, here's the Wormsley number. And if we plot this function, we can actually evaluate this function on the computer. Then we will find what the velocity profile looks like. To this end, I would like to switch now to, let me see how I can do this, to this way. Yeah. Can you see my MATLAB screen now? Okay. So it's a little script, a little MATLAB script, nothing magic, essentially just evaluating the function. And I can call the script with the command WOM, and as an argument, I give it the value of the Wormsley number. So think of the Wormsley number as a frequency. If we start with 110, So I want to evaluate this function here for alpha 10. And that because it's pulsating, I want to animate it over time. Okay, so this is 110. And the red line, you can see now, can you see it? Okay, and the red line is the velocity profile. Moving to the left and moving to the right, coming back. And you see it's not like a Poiseuille profile anymore. Right? Before we have Poiseuille in steady flow, now it looks a bit funny. By the way, the blue line is just for reference. It shows you the pressure gradient, if it's pushing or pulling. Let us start it again. Okay, so the pressure gradient is pushing to the right, but the fluid is only now going to the right. Pushing to the left, and the fluid is lagging behind. The fluid is not fast enough to follow the pressure gradient. It's always a bit behind. It's a bit like the story I said before. It takes the fluid some time to react to what viscosity, what the flow, what the boundary conditions tell it. And this becomes more and more extreme if we increase the Womersley number. Let's go for Womersley 20. You can see that the velocity profile becomes in the center more and more flat. It's an almost flat velocity profile, and that the wall will get sharper and sharper gradients or thinner and thinner boundary layers. Look at this here. See this wavy structure at the wall? This is actually, again, a Stokes boundary layer. That's just close to the wall. Locally, it's like the flat plate that we had oscillating before on the blackboard. It's the same story. Let me go to a really extreme Womersley number. Let's say Womersley 100. That's about what you may have in a cochlea. For those of you who are interested in cochlea, this is what the flow would look like inside the cochlea. Almost flat in the center, only close to the wall. You have a thin boundary layer. And again, the boundary layer scales like 1 over alpha. So for Womersley number 100, you have roughly 1%, 1 over 100, 1% thickness of the boundary layer. Everything else is bulk flow in the center, which is almost flat. Let's go the opposite way. Let's go to a small Womersley number. Womersley, let's say 2, maybe a smaller artery. Okay, now the flow looks a bit more like Poiseuille. It's certainly not a parabola yet, especially in the middle. You see it has a kind of a different shape. It's still not following perfectly the pressure gradient, but we're quite close to it. Let's go to a smaller Womersley number, Womersley 1. Okay, I think this looks almost exactly like a parabola now. So it looks like we are converging back toward Poiseuille flow. If Womersley becomes very small, it becomes like Poiseuille flow. And also, the flow is almost in phase now with the pressure gradient. More extreme, Womersley 0.1. Okay. Now we're almost perfectly in phase with the pressure gradient. So the flow is able to immediately follow what the pressure gradient tells it to do. It's in phase. It is becoming, even though it's oscillating, it is becoming a quasi-steady flow. Okay? So for Womersley going to 0, we end up with a quasi-steady flow situation. We converge or degenerate toward the original Poiseuille solution. And for Womersley very high, do this again. We go the opposite direction. We have a super thin boundary layer. By the way, with very high shear stresses at the wall, because we have a high gradient, velocity gradient to the wall, so we have high shear. And we have a huge phase lag, actually getting close to 90 degrees. Let's go back to the slides. Here you have it summarized again, what I just said with the boundary layer thickness. Again, some pictures just showing you more or less what I've shown you before. the higher the Wormsley number, the more we get something we call a block flow. A block flow is when we have a rectangular velocity profile, right, or a flat velocity profile. This is called block flow. It's the opposite of Poisson. Yes. And here's the story about the resistance. Because the shear layers become thinner, or the boundary layers become thinner and thinner with higher Wormsley, we get more wall shear stress at the wall. We have higher gradients, so it has more resistance. So if we have a certain pressure gradient for a certain Poisson flow, and we increase the Wormsley number, we see on the left there will be less and less and less fluid going through the pipe with increasing Wormsley number. So there's some analogy to electrical engineering. It's a bit working like a coil, right? It's blocking high frequencies. High frequencies have it more difficult to pass through the coil or the inductive element. And there's also the phase lag story. For alpha to 0, we have nearly 0 phase lag, and as alpha increases, the phase lag goes asymptotically toward 90 degrees. So we're 1/4 of a period behind the volume flow. And here everything is summarized. Yes, this is an example. Actually, it's the original paper by Wormsley in 1955 who developed this solution. He measured block flow and pressure gradient in an artery of a dog, I believe, in the femoral artery of a dog. And one curve is the pressure gradient, the other curve is the flow rate. And we see there's a phase lag between pressure gradient and flow rate. The flow rate lags somewhat behind the pressure gradient. And actually, the lag is about 50 degrees in a period of 360 degrees. And we can actually use one of these diagrams I showed 2 slides before. And we see that 50 degrees roughly corresponds to a Wormsley number of 2.7, which happens to be, of course, roughly the Wormsley number in the femoral artery of it. So it just is to show you that this is not just theory, this actually can be found in nature, in vivo. Good. So let's switch over to our main topic of today, which I have here. And this will be much less blackboard, will be a lot more watching movies. Oh, it's here. Okay. Is the slide on, Kai? Yes. Yeah. Okay. Good. So last lecture, or last 30 minutes, it was an exact solution of Navier-Stokes. Now, there's a limited number of exact solutions. And of course, not everything can be solved with exact solutions. And now we're not looking at exact solutions, but we're looking at the case where the Reynolds number is very low, because it's in a very important class of flows, low Reynolds number flows, especially in biomedical engineering. You find a lot of flows in the human body which are low Reynolds. And just to motivate this whole thing, I would like to show you a little video. This is this guy here is G.I. Taylor. It's one of the most famous fluid dynamicists of the last century, or maybe of the whole history of fluid dynamics. And we're going to watch from minute 130 on. Let's see if I can catch that.
Or glacier flow, for which V is small and mu is very large.
Can you please comment if the tone is working?
Note the red flags across the ice field. Here they are 2 years later. Pulling a knife from a pot of honey, for which mu is very large, demonstrates two properties of a viscous fluid. It can resist both tangential and tensile stresses. The honey can only be lifted by a tangential force exerted by the knife's surface, which must be transmitted through adjacent layers of the honey. The stretching of the stream as it leaves the knife gives rise to tensile stresses across horizontal sections. These make the speed of falling much less than if the honey had been falling freely. Though this honey stream shows us something about the properties of viscosity, it doesn't give us any physical insight into the relative importance of viscosity and inertia. A similar set of experiments done with a controlled jet entering a quiescent mass of the same fluid can give us such an insight. In defining Reynolds number, the appropriate length and velocity to be used are the diameter and the velocity of the jet as it enters the fluid. Here the fluid is syrup, and the Reynolds number is 0.05. At this low Reynolds number, the jet hardly penetrates at all. Now let's repeat the experiment using different fluids. The other three boxes contain glycerine, glycerine and water, and water. Each jet will be driven by this piston, and the velocities will be identical. This glycerine jet penetrates to a depth of a few diameters. At this Reynolds number, the jet penetrates many diameters. The tangential force acting on the outer surface of the jet is insufficient to reduce its velocity very much before it reaches the bottom of the box. This jet becomes turbulent Here, for comparison, are the four situations.
Okay, let me stop here, and I think this is a very important picture. We have on the right-hand side, we have the turbulent jet at Reynolds 3000. These are Reynolds numbers you can find in the human body, maybe in the aorta, close to the heart valve. The intermediate cases, I think they were like Reynolds 20 and 200 or something like that. This is a situation you can find in many arteries. It's still laminar flow. It is a complex flow, has some nonlinear effects, but it is a laminar flow. And the one which is rather boring or almost nothing is happening on the very, very left is a low Reynolds number flow. And that's exactly what we're going to talk. And large parts of the human body have exactly this situation, namely microcirculation and capillary flow or flow in the alveoli of the lung. Let me turn off the video and come back here. So how does this look in terms of equations? We have our Navier-Stokes equations here. I would now like to switch to a non-dimensional form of the Navier-Stokes equation that we have looked at, and especially the one where we have a pulsating flow as we usually have in blood flow or also in breathing and many other places in the human body. And we see, especially look at the terms on the left-hand side, that the unsteady term, the term with the UDT, is multiplied by the Wormsley number, and this nonlinear term, the ugly nonlinear term, is multiplied by the Reynolds number. In situations like in a microcirculation or like in the alveoli, the Reynolds number is very small. Likewise, if we were to compute it, the Womersley number is very small. This will allow us to forget, and I'm really now saying forget, about these terms on the left, the first one term, and the second unsteady term. So both can be simplified, can be considered close to zero. This is now not the same as what we have done in the previous lecture. In the previous lecture, we got the exact solutions. There, the terms drop out exactly because of boundary conditions, because of symmetries, and so on. What we do today is a simplification. We assume that for small Reynolds numbers, the contributions of the term on the left-hand side are negligible. What we end up with is a much simpler form of the equations. They're called Stokes equations, not Navier-Stokes, but just Stokes. And they're valid as long as the Reynolds number is small and as long as alpha is small. The continuity equation, divergence of u is 0, still remains the same. Nothing has changed here. What really has changed is in the momentum balance. The only thing that remains is the pressure gradient, which we usually bring to the left-hand side, and the viscosity. So these are the only two things that remain in this equation. What you can see from a mathematical point of view, these equations are much simpler, not just because they have fewer terms in it, but because A, they have no time in it. Time does not appear explicitly in it. And B, the nonlinear term does not appear anymore. And nonlinearity is usually what makes equations complicated and not solvable. One of the main problems of Navier-Stokes is that it has nonlinear terms. The Stokes equations are linear and are much easier to solve because we can use all these tools of linear equations like superimposing solutions and whatnot. The solutions to this equation are called Stokes flow or creeping flow. And both terms are equally valid. Some people also call it laminar flow, which is not wrong, but as you have seen in the movie before, let me switch back. Frames 1, 2, and 3, they're all laminar flow. Stokes flow is only frame 1. Okay, so please don't use the word laminar flow for everything, or use it only for all three. But if it's really low Reynolds, you should only use the word Stokes flow or creeping flow. Let's see. Yeah, let's take a break now. Let's take a break until 20 past. I will switch off the video tool and we start again 20 past with another movie of G.I. Taylor. Okay, talk to you later. The chat is still on. Now we are able to answer questions. Okay, talk to you later. I'm recording again now. So it's a well-posed problem. We can solve this. We can solve the Stokes equations for that. We'll not do this here. It's not as simple as what we have done in the previous lecture. I will just write down some of the results we have for that. Stokes actually did this and wrote down a closed form solution for the flow in a Stokes flow regime. So in a regime where the Reynolds number is a lot smaller than 1. And Stokes found many results for that, but we're just going to write down the result for the pressure P pushing on the surface of this sphere. Right, you can imagine, especially at the upstream side, the pressure is going to push against the sphere P. And the solution that Stokes found is that the pressure P minus the pressure at infinity, so far away we would have the pressure infinity, and close to the wall we have a pressure difference. You can think of this like as the atmospheric pressure. So the difference to the atmospheric pressure is given by the following formula: minus 3 mu over 2a times u times cosine of theta. So it's a relatively simple solution that can be derived from the Stokes equation. And it's worthwhile to look at this a little bit, what it means. So we have this factor in front given by a ratio of viscosity and of the radius, right? We multiply by u, so the faster, the higher the pressure difference. Also makes intuitively sense. And then we have this factor cosine theta. So let's see what this means. So theta starts here. So at this point we have 0 degrees. At this point we have theta 90 degrees, and at this point it's 180 degrees, right? So at this point, theta 0, this is 1. So this is minus 3 mu over 2a times u. So it's a negative value. So we have a negative pressure, so it's pushing, well, it's actually pulling, it's sucking, because the negative pressure is sucking in this direction. As theta is increasing, the cosine decreases until the cosine becomes 0 at 90 degrees. So at this point, the pressure is 0. So we'll go from a high value to a 0 value, or a high negative value, I should say. So we're here in a negative pressure side. On the suction side, and of course the whole thing is symmetric here. I hope I can draw it in a symmetric way. So we have negative pressure on the downstream end, and as theta goes from 90 to 100 degrees, the cosine theta becomes negative, and with the negative sign here, it becomes a positive pressure. So it's pushing into the sphere. Right? And again, it's going from 0 to a higher value, and then back. Right? So here it's pushing all of this value. Okay, and I hope it makes sense to you now that if we're pushing with the pressure and sucking on the other side, we create a net force on it. And that is a drag force that is felt as a drag force. And the total drag force, of course, if you integrate all the pressures over the whole surface, and then you obtain a pressure drag on a sphere in a Stokes flow situation. But that's not yet the whole story. We have another thing that drags on the surface of our sphere. Let us look at the velocity profiles here. This in blue. Right? So we have streamlines here coming. And when we were to look at the profile here, we would see that on the surface of the sphere, velocity must be 0, because on the surface we always must have 0 velocity, no slip condition, and it would be increasing as you go away from the sphere. So we have a pressure gradient, not a pressure gradient, the velocity gradient a non-zero velocity gradient at the wall leading to a shear stress. To shear stress tau, which is creating an additional drag. So we have pressures pushing and sucking, and in addition, we will have on the surface shear stresses. So tangential stresses also pushing or pulling on the sphere. And the sum of all shear stresses integrated over the surface plus all pressure forces integrated over the surface gives us the total drag. And this drag actually does have a famous solution, drag force D. So this is the total, let me give this a different color. On the drag, on the sphere, we do have a total drag force D, which is pushing back the sphere. So this drag force D is given by the surprisingly simple formula 6 pi times mu times A times U. That's it. And let me just quickly check. I don't say anything wrong. And 1/3, so 2 pi mu AU, 1/3 of this drag is coming due to the yellow pressure forces, and 2/3 is coming due to the viscous shear forces, but that's just a detail. At the end, the other thing that is interesting for us is that we have a rather simple formula. We need to know the viscosity of the fluid, the size of the particle, the velocity of the oncoming fluid, or if it's a fluid at rest, we need the velocity of the particle, and we can compute the drag force, and it's all in here. And this is the famous Stokes drag force, or Stokes drag. Let me write it in a different way, and then hopefully you will remember something you have seen a few weeks ago. A few weeks ago, actually, in the very first lecture, we have derived with the Buckingham pi theorem that a drag force can always be written for an object, in that case a sphere, in the following form: 1/2 rho u squared times A being the cross section of the sphere. In that case, for the sphere, this is A squared, right? It's just the cross sectional area, times a drag coefficient CD, and Buckingham pi told us that CD is a function of a Reynolds number, right? This is the fundamental result we have from the Buckingham pi theorem. And we can now try to rewrite this equation, this little Stokes drag formula, in this form, right? We need to expand it by 1u and then put 1u in the denominator, and we need to multiply by a and divide again by a to get an a squared, and so on. So there's a few steps that we have to go through, and I don't want to do it all on the blackboard now. Just back here. Let me just write down what we end up. The end. So we find that we can rewrite the whole equation in this form if we choose CD to be 12 times mu over rho UA. Can check this. If you plug in CD, this value here, you end up exactly with this equation. It's just a regrouping of variables. We didn't really do any math. So what do we have here? This is now a formula what CD looks like based on the Stokes drag. And if we define a particle Reynolds number, let me call it Ray P, Reynolds P, and we define the particle Reynolds number as rho times U times 2A. This is just for historical reasons, we use 2A divided by mu. So it's a particle Reynolds number with the density of the fluid, the velocity of the particle or the velocity of the fluid times the diameter of the particle, not just the radius. We use the diameter divided by mu. If you write it like that, in that case, we can write CD is equal to, because we have now the factor 2 in it, this becomes 24, can be written as 24 over Reynolds P. Okay. So this is the first time now that we arrived from an actual result of what the drag force looks like. We have rewritten it in this Buckingham pi way with a non-dimensional constant drag coefficient CD, and we have been able to show that the drag coefficient indeed is only a function of a Reynolds number. And it's even a simple formula, right? You know now that under the condition that we're in a Stokes regime, the drag coefficient is simply 24 divided by the Reynolds number. It's a rather simple result, and it's valid no matter what fluid you have, no matter what particle you have, no matter what velocity you have, as long as the Reynolds number is small. Right? So that's a really convenient result. And you will see that it can be plotted. Switch back here. Yes. Yeah. You see the slides now, right? We have here the same thing as what we had before, 24 over Reynolds, and you should be able to see now this diagram here. This is how drag coefficients are typically plotted. So this is the drag coefficient of a sphere for all kinds of Reynolds numbers, right? You have Reynolds numbers going up to 10 to the 4, 10 to the 5, 10 to the 6. We're going to talk about this in 3 weeks or in 4 weeks. Today, we talk about the range where we have small Reynolds numbers. And we're in the Reynolds number range, well, this here, the Stokes Reynolds number range, and up here, the drag coefficient in this Reynolds number range is given by 24 over Reynolds. This line here corresponds to 24 over Reynolds. And you see that for high Reynolds numbers, some more complex things are happening. Here, this dip, this has to do with turbulence, but we'll come to that. But that's the real value of these drag coefficients. What else do we need to talk about? Here, this is another funny thing you can do. You can compute the terminal velocity of an object. If you have a particle, for instance, a little aerosol particle in air, it will be pulled down by gravity toward the bottom, At the same time, the faster it becomes, the more it accelerates, the more the drag force will increase. And it will reach a velocity where the drag force is of equal magnitude as the gravitational force, or not of magnitude, is equal, right? And that's the situation when you have a balance, when you have reached a terminal velocity. So when the gravitational force is equal to the drag force, you can put the gravitational force on the left, drag force on the right, and from that you can compute the terminal velocity of a falling particle. Very useful computations you can do. Yeah, we're not going to the Ozene solution, it's not so important. I just want to finish now. I think this is the last, yeah, it's the last slide. I just want to finish now again with a little video from Taylor, who talks a bit about gravitational velocity, and who will also talk about multiple particles. Because this is an extension now. What we did on the blackboard was one single particle, and that's very important. That's a nice result, but it's also useful to understand what happens if we have multiple particles. So another 3.5 minutes of GI Taylor.
Numbers. Here are two brass spheres in syrup. They have diameters in the ratio of 2 to 1. We release one now and the other later.
This is now the configuration where you have terminal velocity. The gravitational
When the smaller ball has one more unit to go, the larger one is released. They reach the bottom mark at the same time. The drag of a falling sphere is proportional to its diameter and to its speed. The net weight of the sphere is proportional to the cube of its diameter. The velocity is therefore proportional to d squared. They have diameters in the ratio of 2 to 1. So the larger one falls in syrup 4 times as fast as the smaller. At Low-Reynolds numbers, the disturbance produced by a moving ball extends many diameters, so that beads far from the ball are moved by its passing. Thus, the presence of a nearby wall can be important. Here are two identical balls, one near a wall and one far from it. The ball near the wall falls more slowly. Incidentally, it remains at a constant distance from the wall, a consequence of reversibility.
Okay, this is again, Stokes drag is what we did for a sphere in open space. So like the situation you have on the right. Walls affect the Stokes drag and ultimately also affect the terminal velocity.
This retarding effect also slows the fall of a particle surrounded by many similar ones, so that a cloud of them falls more slowly than a single one. When a cloud of assorted particles falls in a fluid, it develops a sharply defined top. A particle which has a terminal velocity rather lower than its neighbors doesn't always get left behind. If it did, it would find itself isolated and would fall faster and therefore catch up the rest.
Okay, I'm not sure if you caught that because the voice line is off. So the idea is if these are many particles on top, what is sort of grayish. But these are separate particles in a dense solution. And if one particle is faster, it will get ahead, but it would at the end be slower because the close cloud of particles will catch up with the isolated particle. This is why, in the end, statistically speaking, you maintain a rather sharp line in this configuration.
The left box has many particles. They are close together and the boundary is sharp. The right box has few particles. They fall with less influence on one another and the boundary is less sharp and travels faster.
You see that density of the particles has an effect on the flowing velocity, on the falling velocity of the ensemble. Okay, I think we can stop here. And this is the last thing I had to show on this picture. You see the world of Stokes flow, even though it looks like a more boring situation. Reynolds number is small, equations are linear, but the world of Stokes flow is a very interesting one, and it's highly relevant, especially for you guys as biomedical engineers. This is a special lecture just on this, or special class just on this. Next week, we're going to go the opposite way. Today, we had low Reynolds number. Next week, we're going to go to high Reynolds number. We're going to study the phenomenon of boundary layers, right? Which is a completely different story, but equally relevant. So this ends this lecture. I will stop the recording. And let me see. Stop here. I will stop the recording. And we're going to continue with the exercise class in a few minutes.